Okay, this example. Suppose we want to construct a matrix such that the null space for which the null space NA is the span of these two vectors of V1 and V2, where V1 is this vector 2, 2, 0, 1, 0 transpose, and V2 is this vector 3, 1, 0, 1 transpose. Okay. Now we need to make sure that this null space is exactly this two spanned by these two vectors. Okay. Now we need a matrix such that we want A multiply V1 to be 0, A multiply V2 to be 0. Okay, so this V1, V2, they are column vectors. Now transpose of row vectors is column vectors. So column vectors, if you write in terms of columns, in column vector, so it has 4 rows, 1 column. Okay, so it's a 4 row, 1 column, 4 by 1. So A, to make this product make sense, A should be some row, n row, and 4 columns. Okay, so that the column of A agree with the row number of the vector B. Okay, they coincide. Okay. Now, so first, the two vectors V1 and V2, they are clearly linearly independent. So the null space dimension of V2, so V1 and V2 are linearly independent. So if you look at the last 2 inches of V1 and V2, you will see actually they are actually linearly independent. Linearly independent. So which means dimension of the null space is 2. Okay, dimension. Now number of columns of A is 4. So we need to make sure that, so by the rank-null equation, dimension of the null space plus the rank of the matrix should be equal to the column numbers. Okay, column numbers. So which should be 4. So which means rank A should be 2. Okay, so this 4 comes from column numbers of A. Column number of A. Number of columns. Okay. Now A is rank 2. For column, it has rank 2. Now, suppose if we know the row vector, okay, use the row picture. You see A, if you write A as in terms of rows, okay, it has n row, row 1, row 2, row n. Okay. Now we need to make sure that to make sure AX equals 0, okay, sorry, we need to make AV to be 0, AV1, AV2 to be 0. Now we need to make sure that any vector, row vector R1, Ri, let's use Ri dot product with V1 is 0. I dot product V2 is 0. Okay. Because A has 4 columns, so any row vector should be has 4 components. Okay. So here R, if we write R as 4 component, so suppose this is X, Y, Z, suppose we have T, okay, 4 variables. Then we can write R dot V1. This will be, remember V1, you copy V1 here, V1. So let me copy V1 here. Okay, V1 is 2210. V2 is 3101. Okay, dot product, then we get R dot V1, then we get 2x plus 2y plus 1 times z is z, there's no 0, so this should be 0. And then we have R dot V2, which will be 3x plus y plus no z plus t is 0. Okay. So if we write in terms of matrix form, this will be, right, this 2, 2, 1, 0, 3, 1, 0, oh, 1 times xy zt is 0. Okay. So here A has rank 2. E has rank 2. Rank A is 2. We want to A is rank 2. Also, this matrix, so this matrix B, rank B is also matrix 2. It's rank 2. Then, actually, the solution, the null space, is dimension 2 here, because column space has dimension 4. So we have 2 free variables. Okay, so xy. So we have 2 free variables. Then we can choose, for instance, we choose xy as free variable. Then we solve z as, you see from the equation, this equation, r dot v1. Then we can solve z. Z is negative 2x minus 2y. And then from equation, this is equation 1, suppose, and then from equation 2, we can also solve t. Okay, so we choose xy as free variable. Okay. So you see, the solution, xyz, xyzt is, so xyzt, now it becomes, we can write in this form, xyz plus replace z by xy. Z is negative 2x minus 2y. And t is negative 3x minus y. And then we separate the variable. So right terms that has x, so you write x0, negative 2x, negative 3x. And then separate the y. Okay, no y, y here, negative 2y, and negative y. Okay. Okay, so this will be x okay, factor out x, this we factor out the y. Okay, so you see the space xyz, xyzt, that, you know, orthogonal to the matrix B is actually spanned by these 2 vectors. So when we may take A, for instance, take alpha A to be this vector, spanned by the 2 column vectors with linear combination x and y. So 1, 0, negative 2, negative 3. And 0, 1, negative 2, negative 1. Okay, you check this rank A is 2. Okay, the 2 root vectors are linear independent. Okay, rank A is 2. Rank A is 2. And the root vectors coming from the solution that we solve. So the 2 root vectors is linear independent and is orthogonal to the 2 given vectors v1 and v2. So you see, then the null space of A should have dimension 2, and you know, v1, v2 linear independent and is perpendicular to the root vectors of A. So we see nu A, nu space of A is satisfies the given property. Okay, it's indeed dimension 2. Dimension 2. And we know EV1 is 0, EV2 is 0. Okay, so the nu space is spine. V1 and V2 are linearly independent. V1 and V2 are linearly independent. So we know nu space contains A. So V1 is in nu space, V2 is in nu space of A. Now, this means the nu space is actually spined by these two vectors V1 and V2. Okay, i.e. nu space of A is actually spined by V1 and V2. Then we are done. Okay, more examples. Okay, construct a matrix whose column space construct a matrix A whose column space contains V1, which is a 1, 1, 5. Column vector, we write the column in column. So it's transpose, root vector transpose. And V2, V2 is a 0, 3, 1 transpose. And whose nu space NA contains this vector V3, which is 1, 1, 2. Okay, it's transpose. Okay, now first we look at the column space. The column space is spine contains V1 and V2. Okay. Okay, so because we just construct a matrix set of this property, so we just we can assume that, for instance, the column space is actually spined by V1 and V2. Okay, because we just constructed one example. Okay, not all example. So we just assume that the dimension of the column vector space is 2. We know it's greater or equal than 2, so we just assume it to be 2. So assume, to get one example, assume column vector, column space has dimension 2. So it's a spine dimension 2. So it's a spine by V1 and V2. And we assume the nu space, we just choose the nu space to be the spine. It's a spine of V3. Yeah, it's just V3. So we get rank A is 2. Rank A is 2. Dimension of nu space is 1. Okay. So the sum rank plus dimension of nu space gives us the column numbers. Okay, column numbers. So rank A plus dimension nu space is A. This gives us column numbers, number of columns of A. Number of columns of A. Okay, so a root vector, because the matrix A has 3 columns, so we can assume the root vector, okay, 3 column. So if you write A, it has 3 column, column 1, column 2, column 3. Now, if for a root vector, you see there are 3 components for a root vector. Okay, so let's R to be let's see X, Y, Z. It has 3 components. Be a root vector. root vector of A. Now we need to make sure that the null space, okay, A times V3 is 0. Now, if you use the rule picture, if you write A as R1, R2, we don't know how many rules are there, Rn, for instance, times V3. Now, then you get, then what you get is R1 dot V3, R2 dot V3, V3, dot Rn dot V3. Okay, and this is zero vector. So which means 0 vector. Every component should be 0. So this means the rule, any rule of A, okay, should dot product V3 to be 0. Okay. Now, if we write R as XYZ. Now V3, remember V3 is, we are giving V3, which is a 1, 1, 2 transpose. So R dot V3 will be X times Y plus Y times 1 plus 2 times Z. This is 0. So we get this equation, X plus Y plus 2Z is 0. Okay, remember, the rank of A, rank A is 2. Rank A is 2. So we have 2 free variables. So we can choose Z, for instance, Z as free variable, XY as free variable, Y have XY, X plus Y. Okay, so, okay, now we need to construct this matrix A. Remember, we need a column space contains V1, which is a 1, 1, 5, V2, which is a V2 is given by 0, 3, 1. Okay, now once XY is determined, we write Z uniquely by 1/2 X plus Y. Okay, so we just write V1 as 1, 1, 5. So this gives us the first column. The second column is V2, 0, we choose it to be V2, for instance. So it's a 0, 3, 1. Now the Z component, you see the Z component is determined by negative 1/2 XY, X plus Y. Okay, so the Z component is determined. So the first, look at the first rule, X is 1. The first entry is 1. The second entry is 0. So Z you can write down 1/2, 1 plus 0, negative 1/2. Okay. Now the second column, 1, 3. Okay, X is 1, Y is 3. So Z is 1/2, negative 1/2 X plus Y. So it's negative 2. Okay, negative 2. Now rule 3, X is 5, Y is 1. So Z is negative 1/2 X plus Y. X plus Y is 6, negative 1/2. So we get negative 3. Okay. So you check this matrix A satisfies the given property. Okay.
Professor?
Yes?
So are you just plugging in like the different numbers to fill in the Z column? I just want to make sure that's how you're getting like the negative 1/2, negative 2, and the negative 3.
The component, the third column, okay, the third component is Z component.
Mm-hmm.
Okay,
yes,
the first component, the first rule gives us the X component.
Okay, yeah, and you're plugging in like the X and the Y values to get the Z, right?
Right.
Okay.
Yeah, we plug in, yeah, negative 1/2 X plus Y to get the Z value. Okay,
yeah.
So you see this A satisfies the given property, given requirement. Okay, the rule space contains the column vectors. The column vectors contains V1 and V2. Okay, and the given V3 is in the null space. Okay. All right. Let's do this example. construct a matrix whose column, construct a matrix A whose column space contains the vector v1 to be 1, 1, 1 transpose, and whose null space is the line of the multiple of this vector v2. V2 is 1, 1, 1, 1. Okay, 1, 1, 1, 1. Okay, now we want a matrix. Now here, the column space and the let's see this null space transpose. Okay. Okay, so a matrix multiply v2. V2 lies in null space, means this is 0. Okay. V2 is, if you write in column vector 1, 1, 1, 1. So it's a 4 row 1 column. It's a 4, 1. So we make sure that A has column 4. A should be n row times 4 column. Okay. Make sure the column of A, column number of A agree with the row number of V2, so that we can multiply them. Okay. Same here. Coincide. Okay, A should have 4 columns. Okay, 4 columns. Okay, if you write a matrix A has 4 columns. Okay, 1, 2, 3, 4. Now, you see. Now this means if you do the row vector, a row vector should, horizontal thing should have 4 variable. Okay, so the row vector, let R be a row vector. Let R be a row vector. Let R. So R should have 4 variables. R equal to x, y, z, t. Be a row vector of A. A row vector of A. Now, A multiply then A multiply V2 is 0. Now, if you use the column, if you use the row picture, R1, R2, blah, 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 Rn, dot product multiply V2, this will be R1 dot product with V2. So we get a number. Now, how many numbers are there? We get n numbers. Excuse me. Okay, so this will be n row 1 column. Okay, so to make sure that V2 lies in the null space, we need to make sure that the row vector R1, R2, Rn should be orthogonal to V2. So we need the row vector, any row vector R1, R2, Rn should satisfy. So let's just use the general row vector dot product with V2. V2 should be 0. Okay. Now remember V2 is this. V2 is the vector 1, 1, 1, 1. Okay. So R is x, y, z, t. So R dot V2 is x plus y plus z plus t is 0. Okay. Okay, so now we, you see, if we choose a null space to be dimension 1, okay, the null space is actually the spine of V2. So it's a line. A line is dimension 1. So dimension of null space. Dimension null space is actually 1 because it's a spine of a line through origin O. Okay, null space dimension 1. So column number of A is column 4. So the rank of A, So the rank of A should be 3. Okay, rank A should be 3. Rank A should be 3. Okay, so the only condition is this x plus y plus z plus t is 0. Okay, so so we need to construct rule vectors. So so here we have t is, so we choose t to be negative x plus y plus z. Okay, so we can do the following. So we need to make sure that the rank of A is 3. Okay, so that you see rank A plus null space estimation is exactly 4. Okay, is exactly 4. Here x, y, z, they are free variable. The only condition is x plus y plus z plus t is 0. So x, y, z, they are free. Okay. For instance, we need to arrange x, y, z such that the rule has rank 3. Okay, this is the 4 number of columns. Okay, number of columns of A. Okay, so for instance, contains this. Okay, for instance, we choose this. So the choice of A is far from unique. Okay, for instance, let's choose this one. So we need a vector v1 that is in the column space. Okay, y. Okay, so we can also choose it to be this. So xyz to be y. Now we can also choose, for instance, this one. X is 0, y is 1, z is 0, and x is 0, y is 0, z is 1. So then we get a 0, 1, 0, 0, 0, 1. Okay. Now this actually has rank 3. This is rank 3. The 3 vectors are linearly independent. If you do any linear combination, you cannot get 0 unless you get a 0 combination. Okay. Then once we find x, y, z, we solve z. X, y, z, we solve t. Okay. X, y, z, they are free. So t is, you see, negative x plus y plus z. So actually this you get a negative 1. So x plus y plus z is 2. So we multiply negative 1, so get a negative 2. Now here we get a negative 2. Okay. Okay. So this gives us the condition of A. Okay. Okay. Okay, here you need to be really careful. Now with this condition t to be negative x plus y plus z, we also this it gives one condition that what the matrix A should satisfy. But you need to make sure that the null space cannot be bigger. Here the null space is given as a one-dimensional space. If you, for instance, this one, if you choose this work, this choice we just did, it works. Now this doesn't work. Y. Okay, this negative 3, negative 3, negative 3. You can compute z according to this rule. Z is negative x plus y plus z. Okay, negative that number. Okay, if you look at each rule, y, x, y. So you get to add them together, you get a 3, and then you multiply negative 1. So this only tells you that the null space contains y. Okay, if you do y multiply y, you actually get that thing. Okay, this in the null lies in the null space. Okay, if you check, if you let B to be the thing, v2 to be the thing transpose. So you can actually find v2 is actually 0. However, we can have other thing. The null space is too big in this case. Okay, the null space is too big. You see, the first rule and the second rule are the same. So actually, you can the first column and the second column is the same. So you can do, for instance, v3 to be let's see this 1 negative 1 0 0. So you can also check B times V3 is also 0. So in this case, V3 is also in the null space of B. So this means the null space that for the matrix B is too big. Okay? It not just contains the vector V2. It contains other vectors. So this is because the B has too small rank. B has a rank 1. Okay? Which means null space has dimension 3. Null space has dimension 3 because rank of A is 1. So the root vector of A only span one dimensional space. Rank B is 1. So add them, you get a 4. So we need to make sure that A has rank 3. So to make sure that the three root vectors are linearly independent. Okay. Okay. So homework problem for this section. Let's do number 16 and number 41. I also posted it on Canvas. Okay. Now let's talk about the next section. The complete solution to a linear system. To a linear system, Ax equals B. Let's see, Ax equals B. Now X and B, they are vector. Okay. Now suppose given a linear system, so we have linear system, a linear system. Ax equals B. And suppose we have find a solution. And suppose now we may by trial and error to find the solution x0 is a solution, is a particular solution. i.e. Ax0 is B. Okay. Now for any x that is any solution that satisfies a linear system, then for any x, for any solution, x, we have Ax equals B, also equal to B. Now if we subtract, then use linear property, then we have Ax minus x0 is distribute is B subtract B, which is 0. So this means x minus x0 is in the null space of A. Okay, this vector x minus x0 is in the null space of A. Now, so this is why the null space is so important. It controls the structure of the linear system, the solution of this linear system. Okay. Okay, so we can write down any general solution should be x0 plus a vector plus x1 for some x1 in the null space. In the null space of A. Okay. Okay. Now the question is how do we find actually the solution x0 exists or not? Because here we assume a solution x0. Okay, we don't know actually x0 exists or not. So we assume it exists. But then we find the general solution is actually the particular solution x0 plus any vector in the null space. Okay. Now the next question, how do we find question? How do we find a solution? How to find a particular solution if it exists? How do we find one? How to find a particular solution? Or if there is one, if there exists one, or show that there's none, so that there's no solution. Okay. Now the technique to solve this problem, this kind of problem, is we apply elimination, use rule operations. Okay. Use elimination idea. Use elimination, rule operations. The three types of rule operations. Now let's do one example. Okay, find the condition on B, on the vector B, which is a B1, B2, B3 transpose, for which AX to be solvable. Where the matrix A, we have this linear system, where A is this matrix. 1, 1, 1, 2, -2, -3. Okay, it has 3 rows, 2 columns, so it's a 3, 2. Now, X should be okay. If you write the thing as AX, X should be the vector X should be 2, 1. Okay, 2, 1. So if you write AX to be equal to B, this you get A. Okay, 1, 1, 1, 2, -2, -3 times XY. This equals B, B1, B2, B3. Okay, so you see, we get B1, B2, B3 from the vector XY. Okay, so we get 3 numbers from 2 numbers. Okay, so here we only have very limited choice XY. Then if you produce a lot of examples, then some examples may be related. Okay, that's not too much freedom. Okay, they are not too much freedom because we are, generated from XY, from very limited thing. We cannot get a too big thing. If we get a too big thing, which means they are related. So we should expect some condition on B1, B2, B3. Okay, so this is the idea. So if you write in terms of matrix, so this will be X plus Y equals B1. 1X plus 2Y is B2. Now -2X minus -3Y is B3. Okay, if you write it as augmented matrix, use the augmented matrix. Augmented matrix. We can do it like this. 1, 1, 1, 2, -2, -3. B1, B2, B3. Okay. Now, if you have a bunch of linear equations, you can add them, add 2 rules, or you do the rule operations like manipulated thing. Okay. Now we do rule operations. do root operations. So we get we multiply root 1 by -1 plus root 2. Replace root 2. And then we do negative root 1 plus, we do twice root 1 plus root 3. Replace root 3. Then what we get is do the root operations. Now root 1 is fixed, y1, b1. Now this you get a 0, this you get a 1. This you get a b2 minus b1. Now this you get a here, you get a 0, you get a -1, you get a b3 plus 2b1. Okay. And then we do root operations. We do root operations. Now you let R2 plus R3 replace root 3. So we finally get y1, b1. We get a 0, 1, b2 minus b1. 0, 0, b3 plus b2 plus b1. Now, the third condition, the third line, the third rule tells us that 0x plus 0y, so this is actually 0 equal to b3 plus b2 plus b1, okay? To make sure that this equation is solvable, we need to make sure that b1 plus b2, b3 is actually 0, okay? Okay, so we need 0, we need this condition, b3 plus b2 plus b1 is 0, okay? Then we can use elimination to find a solution, okay? This will be, so we have two variables, two equations. So the remaining thing is invertible, so we can actually find a solution. Then we can, so there's no contradiction anymore. Then we apply elimination. To find a solution. Okay. Okay, so now in this case, you can find a general solution. You can find a general solution. Now the remaining thing will be, you see, the remaining will be x plus y is b1, y is b2 minus b1. So we get a general solution, a special solution. Y is b2 minus b1. X is b1 minus that. So it's x equals 2b1 minus b2. Okay. So here rank of A is the dimension of the root vectors of A. Now the root vectors you see after elimination, so we actually have two vectors, two root vectors, non-zero vectors. So in this case, the space, the root space spanned by the root vectors is actually dimension 2. So rank of A is 2. Rank A is 2. Now, now the column number of A is 2. Number of columns of A equals 2. Okay, so this means new space, dimension of new space is 0 because rank plus dimension of new space is equal to column numbers. So dimension of new space is 0 means the new space contains only 0 vector. Okay, so this means AX to be 0 has only trivial solution. X equals 0. Okay, so we find a general solution. So we find a special solution, and the general solution we can write down. Okay, the null space just the zero vector. Okay. So the general solution is this x general solution. We only have one solution actually. 2b1 minus b2. b2 minus b1. Okay, then we're done. Okay, more examples. Let's see this example. X plus y plus z is 3. X plus 2y minus z is 4. Now, if you write this as matrix, okay, so this will be A x equals B. Now, here we have 3 variables. X is x, y, z. Then you have A is actually write down the coefficient matrix. A is read the coefficients of A of the x, y, z. So the second equation, x 2y negative z. So we get a 1, 2, negative 1. Okay. So this you can do the rule operations. So these 2 rule vectors are clearly not linearly dependent. Okay, they are linearly independent because they are in different direction. You see 1, 1, 1, and 1 to negative 1, different direction. Okay, different direction because one is not a multiple of another. Okay, so A has rank 2. Rank A is 2 because the 2 vectors, rule vectors are linearly independent. 2 rule vectors because the 2 rule vectors are in different direction, linearly independent. They span a plane. So the space that is spine is a plane which is dimension 2. Okay, so rank A is 2. So how about the null space? The null space, rank plus dimension of null space is 3. Here number of columns of A, which is 3. So which tells us the null space is dimension 1 is a line. Okay, null space, dimension of null space is 1. So which means null space is a line through origin, is a line through 0, 0 in certain direction, 0, 0, 0. Okay, so a line we can determine a line, use one parameter, the length. Okay, the length. If we know the direction, okay, if we are given the direction, we can uniquely determine this line, a point on this line by one parameter, the length. Okay, so if we write, we can find a particular solution. For instance, this is very easy to find a particular solution. For instance, you can use trial and error, because here there are many choices. So for instance, we write z as 0. So here, the two equations. For instance, if you let this equation, we let it. So there are many solutions. So you may choose use trial and error, find one, find a special solution. So for instance, take z to be 0. For instance, you can also, for instance, you can take x to be 0. It's also solvable. There are many solutions. We just choose one. Then we get x plus y to be 3. X plus 2y is 4. Then you solve. This is very easy to solve. Okay. So x, you can easily solve x to be 2, y to be 1. You can easily check. So we get a particular solution, a particular solution. Okay, a particular solution. XYZ is, so here XYZ is 2, 1, 0. Okay, now we find a particular solution. Now we need to find the null space of A. Okay, now we need to find the null space. The null space is a line. So the null space, we need AX to be 0. AX to be 0, then you get X plus Y plus Z is 0. Now X plus Y plus Z equals 0. This is a plane. Okay, X plus 2Y minus Z equal to 0. This is another plane. The two planes in different, they are not parallel, then they intersect. Okay, two planes in R3, they naturally intersect if they are not parallel. And then the intersection is a line. The intersection is a line. And you check 0, 0, 0 is the solution. So this intersection is a line through the origin O. Okay. Okay. So, okay, now we solve it. We have certain free variable. So, for instance, we let y minus 2. Then we get we cancel. The reason that we y minus 2 is we want to cancel x. So get a negative y plus 2z is 0. So we solve y is 2z. Now now x by equation 1 by 1, then we get x is negative y plus z, which is negative, replace y by 2z plus z, so which is negative 3z. So if we choose z as a variable, as a parameter, so the general solution, so the null space, so which means the null vector, null space is of the form xyz. So we x is 3, negative 3z, y is 2z, and the z is a z. So null space xyz equals this. Is the null space of A. So the null space is spanned by z, a multiple of this direction. Okay, 3, 2. Okay, 3, 2, negative 3, 2. So this is in the null space. So a multiple of that thing. So we have a direction vector negative 3, 2, and 0. So the general solution. So this is indeed a line. Indeed a line. So the general solution to AX plus B. AX equals B. General solution. General solution is of the form of this form. A special solution. A special solution. For instance, we already get a special solution. 2, 1, 0 plus the general solution z times negative 3, 2, 1. Okay. In plus a vector in the null space. Okay. Okay. So this is indeed a line. Here we translate a line. Now we get the general solution. Okay. Okay, now we talk about a special case. Now you see the solution is actually relative is the dimension of the null space. Okay, the null space. And then the null space, the dimension of the null space is related with the column or the rank of the column space. The rank of the column space. Relative is number of columns. So if for some special matrix, for instance, matrix with full column ranks, then we can get some information about the solution to this linear system. Okay, so we talk about the next case, matrices with full column rank. Matrices with full column rank. Okay, definition. We start with definition. Now the column number is n. Okay, definition. A matrix A has full column rank. Now the column number is n. Suppose then A has n columns. Then the full column rank means all its column vectors are linearly independent, i.e., the space spanned by the column vectors is as large as possible, i.e., n-dimensional space. If all its column vectors are linearly independent, or its column vectors are linearly independent, i.e., they span the largest span a vector space, column space of the largest dimension, linearly independent. Okay. Now the rank, remember rank is rank of a matrix. We have column rank, we can determine the rank by columns. We can also determine a rank of a matrix use rule vectors. Okay. If A is an M by N matrix. Now it has M rule. Okay, it has M rules and columns. Now M rules can at most span M dimensional vector space. Okay. Now N columns span at most N dimensional vector space. So the rank of A is bounded by the column numbers, and by rule number. Okay, so rank of A is less than or equal to the minimum of M and N. So to make sure, okay. Okay, if A has full column rank, this means i.e., rank A equals N, i.e., minimum Mn should be greater or equal than N. Okay, now this means M should be greater or equal than N. Okay, if M is smaller than N, the minimum is smaller than N. So here, i.e., so M is the rules. Okay, so this means we have more rules than columns, possibly. Okay, so this means so we have M rules and column. So M rules, so we have rule 1, rule 2, rule M rules, and the column numbers 1, 2, 3, 4, N. Okay, so this means, so this matrix A has many rules than columns. So this means this matrix is really thin. Okay, really thin. Okay. 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 Now suppose that A is a matrix with full column rank, then we can actually find n linearly independent rule vectors. Okay, we can find n-dimensional n rule vectors that are linearly independent. So you can determine the rank of A use column vectors. You can also determine the rank of A by rule vectors. Okay, the dimension of the rule space, or the dimension of the column space. the dimension are the same, Although we do not, we haven't proved it yet, but this is the fact. Okay, now A has rank n, so which means we can find n-dimensional, n vector space, n vectors that are linearly independent, root vectors. Okay, when we find n linearly independent root vectors. So by root operations, so we can switch the order or switch the position for roots, and then use root operations. So we can finally, so by root operations, we can actually reduce a root operations. We can transform A into this matrix. We may obtain this form. We will obtain this. A use root operations. Remember the 3 types of root operations. And then transform it to this matrix R, which is identity matrix here and 0 here. So here I is identity matrix, n by n identity matrix. And here this is 0 matrix. Okay, 0 matrix. This we have n minus m rows of zeros. Okay. Okay, now we look at the new space. Remember, the root operation, the 3 root operations is invertible. Okay, so if X is a new space, X, if X in new space, this is the equivalent to AX to be 0. Now this means we can do the operation, invertible operation. Okay, so this means Rx to be 0. Okay, multiply the root operation matrix, elementary matrix, because they are invertible. So this is equivalent. Because if you have Ax to be 0, you can do some operation, you get Rx. Okay, you get a 0. From Rx being 0, you can get Ax to be 0 by using invertible operations. Okay, so you get an equivalent the thing. So Rx to be 0, if you write X as this vector. Okay, so here A, remember A is Mn, n columns. So X should be n times 1, n rows, okay? N rows, so it should be this, x1, x2, all the way to xn, this vector, okay? Now Rx being 0, then we have, you see, use the identity matrix, n by n identity matrix. So what you get is actually here identity, 1, 1. So this has n entry, n by n. And here the remaining thing are all 0, okay, are all 0. So Rx being 0, then this is equivalent to, if you multiply this, multiply x1, x2 all the way to xn, then this you get, what you get is x1, x2 all the way to x n. Wait a second, did I get a mistake? Okay, we have m rows n columns. N columns, yes. X is this number of columns is n, yeah. Okay, sorry, my bad. Wait, I mean this. Okay, here, this is okay. Okay, this is n by n. Here, this is the n minus n. This is n minus n. Okay, then this you get this thing, 0, 0, 0. This you get n minus m minus n. Okay, so this vector is 0. So this is vector. So we plug in x n by 1 vector. Then what we get is you cancel this n, you get m times 1. So it's m rows. So this you get n x1 all the way to xn, and then a bunch of zeros, which is m minus n. So this is, you see, n. So it's m row 1 column. Okay, and if this is in the null space, this means everything should be 0, 0, 0, 0, 0. Okay, in particular, this means x1 is 0, the first component is 0, x2 is 0, dot dot dot. This means xn is 0. Okay, so this means the null space can only have the trivial vector 0 solution. Okay, so for a matrix with full column rank, okay, let A be a vector, be a matrix with full column rank. Let A be a full column rank matrix. Full column rank. Then we have the following. First of all, the null space, we know the null space, the structure of the null space completely. That's the null space has only one, contains only one, just the trivial 0 vector, contains only the 0 vector. 0 vector. 0 vector. So we can get information about the solution of linear system. So the second one. Second one. If the linear system, remember the linear system, if it has one solution, if this has a one solution, if you can find a special solution, then the general solution is obtained by the special solution plus any vector in the null space. But the null space has only zero vector. So this means the linear system, if the linear system has a solution, it's possible that it does not have a solution. Then it has only exactly one. Then it has only one. Then it has only one solution. So if you find one solution, then you know that's the only one solution. It has unique solution. Okay, it's possible that it has no solution. Okay, now to find, okay, now this does not answer the question whether it has a solution or not. Okay, to do that, you actually need to do elimination and see if there's a contradiction or not. Use elimination to Q variables. Okay, so this is matrix with full column rank. Now you may ask, what happens for matrix with full row rank? Now let's talk about a matrix with full row rank. Let's see what happens. matrices with full row rank. Okay. Okay, definition. Now we define a matrix that has full rank to be a matrix that all the row vectors are linearly independent. A matrix A has full row rank if all its row vectors are linearly independent. I.e., the row vectors span a vector space of the large dimension, as large as possible, the largest dimension. Okay. Okay. Suppose A is a matrix. Now let A be a full row rank matrix. Then we study certain property of A. What property does A have? Okay. First of all, none of the row vectors is zero vector, because zero vector is linearly dependent on any other vector. So, i.e., A cannot have a row of zeros. Okay. None of the row vectors. No. So A cannot have a row of zeros. Row vectors of A is zero vector. Okay, that's trivial. 2. Ax equals B is solvable for every B. So for full row rank matrix, this is always solvable. The linear system is always solvable. Okay. Okay, now suppose A is, if we write A equals M row n column. Okay, so M row n column, M rows n columns. It has full row rank, so its row rank of A is M, which is the minimum of MA. Less than or equal to. So this means M is less than N, as M is less than N. Okay, minimum of Mn is greater equal than M. So this actually this becomes E. So we get this, we get M equal to the minimum of Ma clearly. So this minimum is less than M. So this means M equals this thing. So actually we know M is the minimum. So M is less than N. So M row, so this means M row n column. M row number is small, okay, rows. And then columns is N, column N. So this means n columns. So this matrix is actually really fat matrix, okay? Fat matrix. Okay, now we have the Rank-Null equation. So Rank-Null equality. Rank of A plus dimension of null space is the number of columns. Column number is n, okay? So you see dimension rank of A. Rank A is, in this case, rank equals m, null space, dimension of null space is n. So we get dimension of null space is n minus m, which is greater or equal than 0. Okay. Now, if m equals n, if m equals n equals m, then A is a square matrix. Square matrix. Square matrix of full rank is invertible. Of full rank, which implies A is invertible. Invertible, so which means AX equals B has unique solution. Has unique solution. X equals A inverse times B. Okay. In that case, the null space is dimension 0. Okay. Okay. Okay, let's do some example. Let's do some example to see what happens. Example. Okay, A is this. 2, 4, 6, 4, 2, 5, 7, 6, 2, 3, 5, 2. Okay, so this is A. Now X is, X is X1, X2, X3, X4, because here we have 4 columns. So then we have 3 rules. So if you write as augmented matrix, then this will be, so the vector B is 4, 3, 5. Okay. If you write augmented matrix, you gotta add this column here. Okay. So this you get augmented matrix. A and this B, put B here. This matrix. Okay. Now we do the rule operations. Rule operations. So use rule operations. Rule operations to do elimination. Okay. So the first column, look at the first column, 2, 2, 2. So we cancel the last 2 entries. So we use rule 1 multiply negative 1 and use that negative thing to Q the first entry in rule 1, in rule 2 and rule 3. Replace rule 2. So multiply rule 1 by negative 1, add to rule 3, and then replace rule 3. So this we get the new augmented matrix. This you get 2, 0, 0. And then 4 is, the first rule is fixed. Okay, the first rule is fixed. Okay, the second rule. Now we use, look at the second rule. 5 minus 4, so we get 1. 3 minus 4, so we get a negative 1. And then here, 7. 7 minus 6, so we get a 1. 5 minus 6, a negative 1. 6 minus 4, so we get a 2. 2 minus 4, so we get a negative 2. And then 3 minus 4, negative 1. 5 minus 4, 1. Okay, so we get this augmented matrix. And then we continue, reduce variable. So use the rule 2, rule 3. You see in rule 2, the first entry is 0, rule 3, first entry is 0. The second entry is 1 and negative 1. So you can add them to Q, 1 entry. So we let, okay, we let rule 2 plus rule 3, replace rule 3. Then we get, what do we get? negative 2, 4, 6, 4. So we do nothing to root 1, root 2. Then we get this is a 0, 0, 0, 0. Okay. So you see, rank of A is actually we have only you see rank of A is actually from the first two vectors, first two rules. You see rank A is actually 2. Okay, the rules of A is actually 0 does not span anything. So the rule space is actually spanned by the first vector, first rule vector, and second rule vector. So this it is spine a plane. So rank A is 2. Rank A is 2. Spanned by the first two rule vectors. Okay. So from AX to be AX to be B. Okay. So we transform to this matrix. Transform this. Did I get it wrong? Yes, it's right. Okay. So we finally transform the thing using the augmented matrix. And then the first rule R1 is actually every entry is a multiple of 2. If we divide every entry by 2, then we get this. Then we get this. 1, 2, 3, 2. 0, 1, 1, 2. 0, 0, 0, 0. And we have negative 2, negative 1, 0. So the last rule is 0. It's bounce 0. It's nothing. So we can so just leave it as it is. So we do rule operation again. Negative 2, root 2 plus root 1. Replace root 1. Then we get 1, 0, 0, 1. Okay. And here this 0, 1, negative 2, 1, 2. And here we have 4, negative 1. Okay, 4, negative 1. Okay, this is bouncer 0, 0. Okay, so in this case, we choose x3, x3, x4 as free variable. Then you see the first rule says x1 plus x2, 0, no x2, 0 x2, plus 0 x2 plus x3 minus 2x4 is 4. So the second rule says x2 plus x3 plus 2x4 equals negative 1. So you can solve x1, x2, so you need to find a special solution. For instance, take x1, x3 to be 0, x4 to be 0. So we get a general special solution. So we get x1 is 4, x2 is negative 1. Okay, so you get x1 is 4 minus x3 plus 2x4. x2 you get a negative 1 minus x3 minus twice x4. So the general solution is a special solution. So a special solution is x1 is 4, x2 is negative 1, 0, 0. Plus the general solution. Sorry, did I? Sorry, I think get a mistake. The general solution. This special solution is right. Special solution is right. Now to find a general solution, actually we just choose the general solution is already there. So we solved from the augmented matrix. So you see the general solution is actually we are all done. So it's a 4, negative 1, 4, negative 1, x3, x4, This is minus x3 plus 2x4. Then this is minus x3 plus 2x4. Okay, so you can write anything as 4 negative 1, 0, 0, plus the terms has x3, negative x3, negative x3, x3, 0, plus the terms that have x4, 2x4, negative 2x4, 0x4. Okay, so we already know the general solution for negative 1, 0, 0. Okay, so you see we have a general solution. The general solution is the special solution plus 2 other vectors. We know the new space is dimension 2. Okay, so you see this is this for negative 1, 0, 0. This is the special solution. Then we have 2. The new space is spanned by negative 1, 1, 0, and another vector. So linear combination x1, x3 of the vector, the 2 vectors that we have here. Okay, negative 1, 1, 0, and another vector is 2, negative 2, 0, 1. Okay, so this is actually the last vector, last 2 vector linear combinations. This span a plane. Okay, they span a plane, dimension 2. So in this case, the general solution is a plane. Okay. So you see, in this case, if a matrix has full root rank, we actually in sometimes we have free variable. Okay. The new space, you can find the dimension of new space, and then you can find free variable. In this case, because here the new space is you can find the dimension of the new space. Then the new space tells us the dimension of the new space is the number of free variables. Okay, you can find a solution, special solution, and add the new space there. Okay, so it's how many the dimension of new space gives us the number of free variables. Okay, in this case, if the new space is large, then the solution set is also large. The solution has the same dimension as the new space. Okay, so if you see, remember the rank, if you use the Rank-Null relation, this is equals column numbers n. So in this case, it's the fact matrix. A is fact matrix. So the number n, column numbers is large. So you see dimension. So this is the column. So the root rank is rank m. So dimension of new space is n minus m. Is n if n is larger than m. This means the new space is so large. So we have a lot of free variables. Okay. Homework for this section. This section is 3.3. 3.3. Okay, for this we choose this number 3, number 4, number 7, number 12, number 18. Okay, now let's go to next section. Okay, this section we already talked about some idea about this, so we just quickly review this idea from section 3.4. independence. Basis and the dimension. We already use this a lot. Dimension. Okay. So we can recall the idea. Recall the idea. We can use a set of vectors is linearly independent. Vectors. They are linearly independent. V1, V2, all the way V1 is linearly independent. If there are no relation between them, i.e., any relation is trivial relation, i.e., if their linear combination is 0, is possible now, which means only the trivial relation. If they span 0, then the coefficient should be 0. Okay. I.e., you cannot express a vector as a span of other vectors. I.e., you cannot generate a vector by other vectors. So they are, in some sense, they are free. This vector is free. There's no relation between the vectors. So in that case, the space that they span is as large as possible. The dimension of the space that is span is large as possible. So theorem. Let A be a matrix. Then the column vectors, the column vectors of A are linearly independent if only if the linear system has only the trivial solution, are linearly independent. Is equivalent to if only if the linear system AX equals B equals 0 has only 0 solution, has only the trivial solution, i.e. X equals 0. Okay, now this is very easy to see. Now, if you write the A as column picture, columns, okay, and then X as X1, Xn, okay, then A dot product A multiplied the matrix A multiplied the vector X will be X1 C1 plus X2 C2 plus Xn Cn. This is 0 vector. Now this vector linear combination of the column vector is 0. But here we know the column vectors are linear independent. So the only relation linear combination you get 0 is only possible is equivalent to X1 equals X2 equals Xn equals 0. Okay, because C1, C2 are linearly independent. Are linearly independent by definition. Linearly independent. Okay. So we're done. Okay. Then we're done. Okay, some example. Example, if we have two vectors are linearly independent if they are not in the same direction. They are not in the same direction. Two vectors, V1. Independent. Okay, if they are linearly dependent, which means they are in the same direction. They can only span a line. They cannot span a plane. Okay. So if they are not parallel, they are not parallel. So we can use so this, parallel is geometric condition. So we can use vectors to study geometry. So actually, vectors is really good to study geometry, like a parallel, like a perpendicular. So this means V1, V2, V2, span a plane. Okay, span a plane. So lambda V1 plus lambda V2 is 0, which implies lambda 1 equals lambda 2 is 0, equivalent. Because if one of them is non-zero, then you have V1 is a multiple of V2 or V2 is multiple of V1. So this means they are in the same direction, which are not possible. Okay, now example. If we have three vectors, then they are linearly independent if they span a three-dimensional space. Then they span a three-dimensional space. If they are linearly dependent, which means they do not span the R3, which means they should lie in a plane. Okay, example. If three vectors V1, V2, V3 are in the same plane, in one plane, in the same plane, they are not linearly independent. They are dependent. So you can use some relation, V1, let's see, V2. You can use some relation. Suppose V3 is this direction, V3. So you see V3, you can have some lambda V1 plus lambda 2 V2. Okay, so you see, we can choose, for instance, we can choose lambda 1 V1 plus lambda 2 V2 minus plus negative 1 V3 to be 0. So you have a non-zero solution. Okay, lambda 1, lambda 2, and negative 1. So this linear combination, you get a 0 vector. So this means, so this is non-trivial solution. Non-trivial relation between the three vectors, between V1, V2, V3, which means they are not free. They are actually dependent on each other. Okay. Okay. Now, so think about this question. So in a plane, okay, any three vectors in R2, any three vectors, they naturally lies in R2, lies in this plane. So three vectors in R2 should be linearly dependent, okay? So if you have n vectors, so n plus 1 vectors in Rn. Rn is dimension n, okay? Now you have n plus 1 vectors. If they are linearly independent, then they span a dimension n plus 1. But they live in Rn. This is not possible, okay? So this means n plus 1 vectors in Rn should be linearly, are linearly dependent. If they are linearly independent, they span two large space, but the space that they live in is Rn, okay, is small. So they are actually linearly dependent. Okay, the idea is like the pigeonhole principle. If you put n plus 1 object into n drawer, then one of them should have at least 2. object. Okay, if you put 100 objects into 99 drawer, then one drawer should have at least 2 objects. This is called pigeonhole principle. This is n plus 1 vectors in Rn should linearly dependent. Same idea. Okay. Okay. Now, if you have n plus 2 in Rn, n plus 2 vectors in Rn, is of course they are linearly dependent. Okay. Okay. Here is definition of basis. Now you see linearly independent vector, this spine certain thing. If they are linearly dependent, then there's a redundant thing. The definition of basis. So a basis is just okay, no redundant and linearly independent. So a basis for a vector space, okay, is a set of linearly independent vectors that span the space. Okay, if we have too few vectors, now it is spine too small space. So this does not form a basis. Now, if we have too many vectors, then there are maybe relations between them. So there are redundancy. So this is not a space, a basis. So to be a space, we need to make sure they generate the space. And second, it's linearly independent. Okay, the set of vectors should be linearly independent. Linearly independent vectors that span the space. So a basis is just okay. Okay, the minimum number of vectors that span the space. Okay. Next time we will continue with the definition of vectors of basis and study some property of basis. Okay. Let me maybe stop here for today and continue tomorrow.